most dangerous construction race on Earth is not for the tallest tower, the fastest train, or the biggest dam. It is for a building with no windows, no glamour, and almost no room for error. A semiconductor fab looks quiet from the outside. Inside, it decides who builds the servers that train artificial intelligence, who equips the militaries of the future, who controls the electronics in cars, grids, hospitals, data centers, and missiles, and who gets to shape the next era of global power. That is why the US-China chip war is no longer just a trade dispute. It is an industrial mobilization. It is a race to pour concrete, install tools, secure water and electricity, train workers, lock down supply chains, and build entire technology ecosystems before the other side closes the gap. And the scale is staggering. Chips for America says semiconductor and electronics companies have announced nearly $450 billion in private US investments. Semi says chip makers are expected to spend a record $400 billion on manufacturing equipment worldwide from 2025 through 2027. China, meanwhile, created a new state-backed semiconductor fund worth 344 billion yuan, or about $47.5 billion, while continuing to lead the world in regional chip equipment spending. This is why people talk about a trillion-dollar chip war. Not because one contract carries that number, but because the spending race now stretches across factories, tools, packaging plants, materials, subsidies, utilities, and strategic stockpiles. On the American side, the vision is spread across several giant clusters. TSMC has expanded its U.S. commitment to $165 billion in Arizona, adding 3 more fabs, 2 advanced packaging facilities, and an R&D center on top of its earlier plans. Intel's CHIPS award was tied to an expected U.S. investment of nearly $90 billion by the end of the decade. Samsung's Texas project alone is expected to exceed $37 billion and includes 2 leading-edge logic fabs and an R&D fab. The CHIPS and Science Act itself provided the Commerce Department with roughly $50 billion to rebuild U.S. semiconductor research, manufacturing, and workforce capacity. On the Chinese side, the goal is just as clear. Survive the choke points, replace foreign tools where possible, and keep moving up the technology ladder even under sanctions. Reuters reported that China remained the top regional spender on chip-making equipment in 2025, and Beijing's new Big Fund 3 is the largest phase yet of its state-backed semiconductor push. This is not just about making more chips. It is about making sure China cannot be technologically contained by a handful of foreign governments and a handful of foreign suppliers. But before any ribbon cutting, before any clean room, before any Made in America headline or self-sufficiency slogan, the real battle begins in the planning phase. A modern fab cannot simply be dropped onto cheap land and expected to work. Developers have to run feasibility studies on power reliability, grid access, water availability, wastewater treatment, freight access, labor pools, seismic and vibration conditions, and the distance to suppliers and customers. Environmental reviews for U.S. CHIPS projects examine climate impacts, air quality, water resources, transportation, land use, noise, biological resources, hazardous materials, human health and safety, environmental justice, and socioeconomics. Federal guidance also requires applicants to map out environmental permitting steps, risks, and mitigation paths before construction can stay on schedule. That early work matters because a fab is less like a warehouse and more like a precision ecosystem. geology is wrong, vibration can ruin production. If the water strategy is weak, the site becomes politically vulnerable. If the power plant is incomplete, billions of dollars in tools can sit idle. If permitting slips, the schedule collapses long before the first wafer exists. In this industry, mistakes made during surveys, approvals, and design revisions do not stay on paper. They show up years later as delays, weak yields, missed customer commitments, and cost overruns that are almost impossible to hide. Then comes the moment the project becomes real. The site is cleared. Fences go up. Temporary roads and staging yards appear. Site offices, utility hookups, drainage, and logistics areas are built before the actual fab even starts to rise. Heavy machinery rolls in. Excavators, cranes, concrete fleets, piling systems, chillers, compressors, and the specialized handling equipment needed for oversized industrial cargo. On these sites, the work is not just about buildings. It is about creating a controlled industrial city that can feed chemicals, gases, electricity, cooling, clean air, and ultra-pure water into one of the most sensitive manufacturing environments ever built. Intel's own numbers show just how physical this is. A single Intel factory can cost about $10 billion, take 3 to 5 years to complete, and require around 6,000 construction workers. Intel says building one fab can involve removing more than 1 million cubic meters of soil and rock, pouring 600,000 cubic meters of concrete, installing 75,000 tons of steel reinforcement, adding 35,000 tons of structural steel, and laying 9 million meters of cable. Even the heaviest cargo matters. Intel cites a 50,000 kilogram chiller as one of the major loads brought onto a fab site. In Arizona, Texas, and Ohio, that physical build-out is tied to a broader strategy. Arizona is becoming a logic and packaging cluster around TSMC, Intel, Amkor, and Arizona State University-linked R&D activity. Texas is being positioned as Samsung's leading-edge ecosystem, with both production and research. Ohio was meant to become a new Silicon Heartland anchored by Intel's giant campus in New Albany. The map itself is strategic. Spread risk, build redundancy, and stop relying so heavily on one part of East Asia for the world's most important chips. Once earthworks and foundations are finished, the fab rises in layers, and that is where semiconductor construction starts to look unlike almost any other mega project. Intel describes a fab as having 4 levels. At the top sits the interstitial and fan deck, where air systems keep the clean room at the right temperature, humidity, and particle control. Then comes the clean room level itself, packed with more than 1,200 factory tools that process silicon wafers. Below that is the clean subfab, filled with thousands of pumps, transformers, cabinets, and support systems. Underneath sits the utility level, carrying the mains, the large pipes, ductwork, chillers, and compressors that keep the entire machine alive. That construction sequence is brutally unforgiving. Civil engineers, structural teams, electrical contractors, pipe fitters, HVAC specialists, gas delivery experts, waste treatment crews, safety teams, and tool vendors all have to work in a precise order. Utility corridors must line up with laterals. Exhaust and chemical systems must connect to the exact tools they will serve months later. The concrete and steel must support vibration-sensitive production above them, and all of it has to be finished in a way that allows the most expensive machines on Earth to move in without contamination or delay. This is why the engineering challenge is so hard to overstate. A fab is not just a building that contains machines. It is a machine that contains machines. Intel says a typical fab includes 1,200 multi-million-dollar tools and 1,500 pieces of utility equipment. Reuters reports that an advanced semiconductor production line needs more than 3,000 tools across patterning, process, and inspection. One weak link can spoil the output of the entire line. One dust particle, one vibration issue, one power fluctuation, one contamination event can destroy wafers that have already passed through dozens or even hundreds of processing steps. And then there is water. Intel's Fab 34 project in Ireland gives a sense of how seriously chipmakers treat it. Intel says the site includes an advanced ultra-pure reclaim water system that conserves more than 275 million gallons of processed water per year. That matters because chips are built in environments where wafers must be cleaned repeatedly with extremely pure water, while the fab also manages heat, chemicals, and exhaust at industrial scale. The political argument about chips is often framed around AI and military power, but the engineering argument often comes down to water loops, chillers, filtration, and waste treatment. Then comes the tool bottleneck, the part of the story that turns construction into geopolitics. ASML remains the world's only supplier of the most advanced EUV lithography systems. Reuters notes that the US has blocked EUV sales to China since 2019, forcing Chinese firms to rely on less advanced DUV systems to push towards 7-nanometer production. In December 2024, the US tightened controls again on a broader range of semiconductor manufacturing equipment, software, and even high-bandwidth memory, or HBM, the memory critical to large-scale AI training and inference. ASML itself said the updated rules could affect additional fab locations, mainly in China, and could also hit some DUV immersion shipments depending on Dutch decisions. That means the chip war is being fought at multiple levels at once. America is trying to build more fabs at home while controlling the flow of the machines needed to build the most advanced chips abroad. China is trying to build around those controls by buying, stockpiling, localizing, reverse engineering, and funding domestic equipment champions. And the rules themselves keep moving. BIS tightened foundry due diligence rules again in January 2025, and in January 2026 revised license policy for some advanced chips exported to China, showing that this is not a fixed battlefield. It is a live one. The economic stakes are just as large as the technical ones. TSMC says its expanded U.S. investment is expected to support 40,000 construction jobs over 4 years and generate more than $200 billion in indirect economic output in Arizona and across the United States over the next decade. Samsung's Texas project is expected to support more than 15,000 jobs in the region. NIST says chips-related announcements across more than 20 states are expected to create over 125,000 jobs. The customers are not obscure. TSMC's Arizona fabs are tied to companies like Apple, Nvidia, AMD, Broadcom, and Qualcomm, which means the chip war reaches straight into the heart of consumer electronics, cloud computing, and the AI boom. China's side of the ledger looks different, but no less serious. Reuters reported that China bought $41 billion worth of wafer fab equipment in 2024, accounting for 40% of global sales. Even as analysts warned of overcapacity in some segments, Chinese equipment makers like Nara and AMEC have expanded rapidly. Reuters also reported in March 2026 that Huahong Group's Huali Microelectronics was readying a 7-nanometer process in Shanghai, which, if realized at scale, would make it China's second domestic chip maker at that level after SMIC. But this is also where the risks and controversies begin to pile up. Intel's Ohio project is the clearest warning sign. In February 2025, Reuters reported that Intel's first Ohio fab would not be completed until around 2030, with operations starting in 2030 or 2031, while the second fab would complete in 2031 and start running in 2032. The site is still under continuous construction, and Intel says the fabs are going vertical. But the schedule slip is dramatic. A project that was once sold as urgent can become a symbol of just how difficult it is to convert political will into production capacity. Samsung's Taylor site shows a different kind of vulnerability. Reuters reported in October 2024 that Samsung had delayed taking deliveries of some ASML equipment for the Texas fab, even as the company said its plan to start production in 2026 had not changed. NIST's project page now says Samsung's Texas facilities are expected to be operational by 2030. That gap between announcement, construction, equipment arrival, qualification, and actual production is exactly where chip megaprojects can drift off course. Environmental and operational risk never disappears either. Semiconductor environmental assessments specifically review water, noise, transportation, hazardous materials, human health and safety, and environmental justice. Intel's Arizona Environmental Assessment notes common semiconductor chemicals including hydrofluoric acid, sulfuric acid, solvents, and other materials that require careful handling. So even when a fab promises jobs and prestige, local communities still have to live next to high-intensity industrial infrastructure that consumes major resources and depends on strong safety and compliance systems. And even when the concrete is done, the project is still not truly finished. Last stage is testing, commissioning, and yield ramp. Tools have to be moved in, installed, calibrated, and qualified. Clean rooms have to prove they can maintain stable temperature, humidity, and air purity. Chemical and gas systems have to pass inspection. Safety and regulatory requirements have to be satisfied. Then comes the hardest test of all. Can the fab make large volumes of good chips consistently at a cost customers will accept? NIST's CHIPS Awards are milestone-based for exactly this reason. Construction is only one milestone. Technology, production, and commercial targets come after. TSMC's Arizona timeline shows how long that handoff takes. Reuters reported that the first Arizona fab began volume production in the fourth quarter of 2024 using 4-nanometer technology. The second fab had completed construction, with tool move-in planned for 2026 and volume production expected in the second half of 2027. The third fab broke ground in April 2025 and is targeted for 2-nanometer and more advanced technologies by the end of the decade. In semiconductor terms, that is fast. In political terms, it still feels painfully slow. If this strategy works, the consequences will be enormous. NIST says the United States is on track to produce at least 20% of the world's leading-edge logic chips by 2030, up from 0 in 2022, and roughly 10% of leading-edge DRAM by 2035. It also says the US could have 8 new leading-edge logic fabs by 2030 and at least 3 high-volume advanced packaging facilities. That would not end Asia's dominance, and it would not make chips cheap, but it would give the United States something it has not had in years: a real domestic position in the most strategically valuable layer of modern manufacturing. If China's strategy works, the balance shifts in a different way. China may still lag at the frontier, especially in lithography, but it could become far harder to contain. Domestic equipment makers could fill more of the supply chain. Mature node overcapacity could translate into long-term global market share, and if reported progress at firms like Huahong turns into reliable production, then the sanctions regime will look less like a wall and more like a delay. But if the project fails on either side, the fallout will be brutal. For the United States, failure would mean expensive shells of industrial nationalism, giant campuses delayed by years, subsidy politics without enough output, and a continued dependence on overseas manufacturing even after hundreds of billions of dollars in announcements. For China, failure would mean overcapacity, weak yields, trapped capital, and continued dependence on foreign bottlenecks for the most advanced lithography and tooling. Reuters says China's self-sufficiency ratio for equipment capable of making 7-nanometer or smaller chips remains below 10%. That is not a small weakness. It is the pressure point the entire war keeps circling back to. And for the rest of the world, failure on both sides would mean something even worse. Higher chip costs, slower AI deployment, more fragile supply chains, more political coercion, and an even more dangerous dependence on whatever single region remains able to manufacture the most advanced chips at scale. Because in the end, the US-China chip war will not be decided by speeches, sanctions lists, or groundbreaking ceremonies alone. It will be decided inside silent buildings where the air is filtered, the floors cannot shake, the water must be purer than nature can provide, and a civilization's future is written one wafer at a time.